Picture yourself on the edge of a vast cliff. The Milky Way is behind you. 400 quadrillion stars. Everything people have ever learned, every society that could live in it, and every world we could ever hope to visit. And nothing in front of you. A space so big that Andromeda, the next big galaxy, is 2.5 million light-years away. This is the scary part. In this universe, the speed of light is the fastest thing that can move. If we could travel that fast, it would still take longer than the entire history of people on Earth. So, what chance do we really have of getting across that distance? For what reason does science seem to want to keep us stuck? Let's start with distance, which we think we understand. We've already talked about traveling between stars. Proxima Centauri is 4.24 light-years away and is our closest star neighbor. The Parker Solar Probe, which is our fastest probe, would need more than 6,000 years to get there. That seems impossible already. Let's zoom out now. 4 light-years is not how far away the Andromeda galaxy is. 2.5 million light-years away. That number is not bigger. It's a different kind of number. One that changes the way our minds think about size. Let me try to make this real. It would take about 600,000 steps to get from Proxima Centauri to Andromeda, instead of just one. It would take that long to walk from New York to Los Angeles twice, plus some. Or look at it this way. When light moves at 300,000 kilometers per second, it takes a little more than 4 years to get to each other. It takes that light 2.5 million years to get to Andromeda. People in the past hadn't found fire yet when the light from Andromeda started its trip to night. They didn't have any language yet. They were very similar to other monkeys that lived in the African desert. Still, Andromeda is thought of as our friend. It is the main galaxy that is closest to us. Distances get even stranger after that. Things get worse from here on out. There's a wall that no amount of engineering could get around, even if we were able to build a spaceship that could move at a significant fraction of the speed of light. The math behind rockets. Spaceships need fuel to work. That power has weight, and to speed up that mass, you need more fuel, which has mass and needs more fuel. Any attempt to go fast is met with a vicious exponential cycle that makes things worse. It would take more energy than whole countries use in a year to speed up even a small spaceship to 10% of the speed of light. All of that is just speeding up. When you get to your goal, you have to use the same amount of energy to slow down. At gaps between stars, this is already a problem that is almost impossible to solve. Up to a certain distance, it's not a problem. That thing is a wall, a solid wall. It takes more energy than stars give off to speed up a spaceship to a level of speed that would allow it to travel between galaxies in an acceptable amount of time. We're not talking about technical limits that might be broken by people in the future. We're talking about the basic business of physics. The rocket equation doesn't care what your goals are. You might now be asking, what about other ways to move? What about ion engines, nuclear drives, or even stranger ideas? Let us go over them. Ion engines work amazingly well. Using electric fields, they speed up charged particles and can keep working for months or even years. NASA's Dawn probe did a great job of showing how well they work. But there's a catch. Ion thrusters don't make much power at all. They're great for slowly speeding up over long amounts of time in our solar system. For a trip across the galaxy, that low thrust means it will take hundreds of years just to hit cruising speed. After all that time, cruise speed would still be a very small part of what we'd need. It is stronger to use nuclear heat propulsion. A reactor heats hydrogen to very high temperatures, which gives the rocket a lot of power. Chemical rockets are about twice as effective as this one, but that's still not nearly enough. We don't have a problem that can be fixed by making everything twice as efficient. The amount of energy needed goes up as the speed squared. To get there twice as fast, you need 4 times as much energy. The math is very hard. Ion technology is added to nuclear electric devices to make them even better, more complex and efficient. Still not even close. The bigger problem is that all of these methods are small improvements on approaches that are already very limited. They make it easier to move between planets. They might one day be able to support trips between stars that last decades or centuries, but the numbers just don't work for travel between galaxies. What about ships from the next generation? This is often suggested as a way to move between stars, huge ships, which were basically self-contained worlds where generations of people would live, have children, and die during a long journey. The first crew would never get to their goal. It's possible that their distant ancestors would use this to go on a trip to Proxima Centauri. Several thousand years, which is hard to imagine, but possible if we could figure out the mechanical problems. Andromeda, though, think about what we're really suggesting, a trip that lasts 2.5 million years. That's not time periods, that's time in geology. That's how long it took for people to change from our last hominid ancestors. A generation ship going to Andromeda would have to be able to keep a population going for longer than our species has been around. The social problems are already huge. How do you keep a society running for millions of years? How do you keep information alive for 100,000 generations? How can you stop a total breakdown of society, a civil war, or just the loss of purpose over long periods of time that make human history look like a footnote? Every kingdom that people have ever made has fallen apart in no more than a few thousand years. We want a single ship stuck in the space to keep a society running for 1,000 times longer than any other society has ever been able to. That is, if the ship doesn't break down. No machine that people have ever made has worked for more than a few decades without major repairs. What we're suggesting is a ship that should work perfectly for millions of years. All of the systems that recycle, lock, and make things work would have to be perfect for as long as mountains stand. The idea is not only useless, it's also wrong in a category. We're trying to solve problems that happen on cosmic timescales with answers that work on human timescales. Let's take a moment to fully understand what we're facing. It takes 2.5 million light years to get to the Andromeda galaxy. From the point of view of someone outside the journey, it would take about 2.5 million years, even if they traveled at 99% of the speed of light, which is impossible with any technology we can think of. One strange comfort does come from special relativity. Travelers going that fast would feel like time was moving faster than it really is. From their point of view, the trip may have seemed like decades instead of thousands of years. But this makes things even more difficult. In the harsh conditions of intergalactic space, no life support technology could keep a crew alive for decades. Over such long periods of time, no spacecraft could protect its people from the impacts of cosmic radiation. As we've already talked about, the human body isn't made for long-term space travel. Bones get weaker, muscles lose mass, hearts get smaller, and eyes get worse. That's only for trips that last a few years. A journey that lasts decades through the empty space between galaxies, far from any star or planet, and with no way to get supplies or help. It's not hard to do this. It's like the death penalty with more steps. Things don't get better, though. Space between galaxies is not empty. People often think that, and it's not true. The space between galaxies is made up of gas, dust, and particles. At the speeds needed for any real intergalactic travel, even the smallest piece can cause a huge problem. If something as small as a grain of sand hit a spacecraft going at even 10% of the speed of light, it would have the force of a small bomb. The devastating potential grows exponentially as the speed goes up. To protect against these kinds of collisions, you would need a lot of mass. That brings us back to the fuel issue. It takes more fuel to move more mass. It takes more fuel to make something bigger. The loop keeps going and the numbers stop making sense. Finding your way around is another major problem. We can at least use faraway stars as guides in outer space. Some of these points of reference get fewer and less bright as you move farther away from galaxies. And there would be no way to communicate. If a spaceship could make the trip, it would be completely alone. It would take 2.5 million years for a letter sent back to the Milky Way to get there. It would take another 2.5 million years for the answer to come back. Any ship that crossed that void would be farther away from other stars and planets than any person has ever been or could ever be in our own galaxy. The psychological aspect is also something that most people don't think about. You could still see stars in our galaxy, even if you went on the longest possible trip. The sky at night would look different, but it would still be clear that it was a sky. There would be points of light all around you. In some way, you'd feel like you were still a part of something. That comfort goes away in cosmic space. Behind you, the Milky Way's stars would look like a small dot. The stars of Andromeda would stay a smudge in the distance, and there would be nothing in the space between them. There is such complete darkness that it makes the emptiest parts of our galaxy look busy. True nothingness has never been felt by a person. The sky can be seen even in the most remote parts of Earth and on the dark side of the moon. Something like stars or clouds. In the cosmic void, you would float in such total darkness that you wouldn't even be able to figure out which way to go. For years, decades, or even generations, if anyone could make it that long. Astronauts who have been to the ISS for 6 months say that being alone, confined, and far away from everything familiar is hard on their mental health. They can still see Earth. They are still able to talk to home right now. Imagine that stress lasted for millions of years, and there was nothing but blackness in every direction, neither home nor goal. The mind wasn't made to do that. There was nothing. That might seem like the hardest part. It's not. There's something even more basic that is against us. The world is getting bigger. Furthermore, it is not only growing, but also growing faster. Andromeda is one of the few galaxies that is moving toward us because their gravity pulls them together. It will crash into and join with the Milky Way in about 4 to 5 billion years. But everything farther away from our group of galaxies is going away, and galaxies move away faster as they get farther away. There is something disturbing about this growth. Beyond a certain point, galaxies are moving away faster than light. That's not because they're going faster than light, which is impossible. It's because the space between us and them is getting bigger. Faster than light can travel through it. This sets a cosmic horizon, a line that no matter how great our technology gets, we will never be able to see, talk to, or reach anything beyond it. And now, the grim truth. This edge will get closer over the next 100 billion years. As space keeps expanding, galaxies that can be seen now will become less noticeable because their light will be stretched into wavelengths that can't be seen. In the far future, people looking from far away will eventually only be able to see their own group of galaxies surrounded by total darkness. They won't even know there are other galaxies out there. It looks like the world is meant to get lonelier. What does this mean for us now? Some thinkers talk about ideas that are on the very edge of what we know about physics. There are wormholes, the Alcubierre drive, and ways to change reality itself. Let's be sure we know what these are. Wormholes are thought to be shortcuts through space-time, like tubes that could connect faraway places in the universe. They come from the math behind general relativity, but there is no proof that they exist. And even if they do, keeping one open would require strange matter with a negative energy density, which might not exist at all or would go against basic physics. The Alcubierre drive is an even stranger idea. It suggests making space smaller in front of a ship and bigger behind it. This would let the ship travel faster than light without officially going over the speed limits in the area. What's the catch? The amount of energy needed would be more than the mass energy of a star, maybe the mass and energy of the universe we can see, and it's not even clear that the idea makes sense physically. You should use math to look into these ideas. They help us learn more about physics. But they aren't answers. They're just ideas, and thinking of them as possible tools in the future isn't taking into account how far away they are from being real. This is what we know for sure. It takes 2.5 million light years to get to the Andromeda galaxy. We can't even begin to imagine how much energy would be needed to travel that far. The amount of time required is orders of magnitude longer than the history of human civilization. Intergalactic space is dangerous. We are alone, and the universe is expanding. All of these things work against us. There is no getting around physics. But here's what's really interesting. We don't need to go there to study it. We can see Andromeda in great clarity with telescopes. We can look at its light, make a picture of its structure, study its stars, nebula, and the very large black hole at its center. We can see it coming toward us through the void of space. The James Webb Space Telescope and other future telescopes will show us things about faraway galaxies that were impossible to imagine just a few decades ago. We don't have to cross the universe to study it. It might be depressing to think that we are so very, very small as a single galaxy in a universe with trillions of galaxies. At most, our reach includes our great friends, and even that is a huge accomplishment. But our interest goes further. Our tools go farther. We know things that are billions of light years away. We might never be able to walk among the stars in Andromeda. It's possible that we will never send a probe to these worlds. We can know it, though. We can be amazed by it. We can figure out where we are in relation to it. And there is something very deep in that understanding. The universe doesn't owe us access to everything in it. It's just the way things are. It's just the way physics works. The galaxy we have is what we have. 400 quadrillion stars, billions of possible worlds. There is enough mystery and wonder in the world to keep our species busy for thousands of years. If we make it that long, that could be the real lesson. Not that the universe is curly huge, but that what we have is so rich, it's hard to believe. It's already too much for us to fully explore and learn about all of them together. Physics walls keep us in the Milky Way, which is also our home, our cosmic neighborhood, and the place where our story, whatever it is, will take place. Andromeda will keep moving toward us. It will join with our galaxy in a very long time. There will be new stars and worlds coming together. And if there are any heirs of humans, they will see how the sky has changed, but they still won't go to other galaxies. The walls are staying up, which might be fine. I hope the video was fun for you. If these ideas interested you, you might want to subscribe.